So in this video, we're going to look at two short concepts that are in the heat chapter, and it is the solar constant and U values. So for solar constant, I'm actually going to explain it through a question first, because I want to kind of show you how important it is to understand units and what units mean, because you don't even need to know what the solar constant is, but you can actually answer this question if you understand units. So we have a house and it has a square solar panel at the side 4 meters. So here's our solar panel and it's of side 4 meters. So that means it's 4 meters is one side, 4 meters is the other side. If the sun is shining perpendicularly on it, so the sun is shining like this on it for 6 hours, how much energy is incident? So that incident means is falling on it. If the solar constant is 1.35 kilowatt per meter squared. Now we don't know what solar constant is yet, but if you look at these units, you should be able to figure that out. So solar constant is 1.35 kilowatts per meter squared. Well, let's break down what that means. What's 1.35 kilowatts? Sorry, 1.35, not 1.5. 1.35 kilowatts is 1,350 watts. What's a watt? Well, a watt is 1 joule per second. So that's 1,350 joules every second. Now, where did I get that joules per second from? Well, power is energy over time, which is joules per second. So 1 watt is 1 joule per second. So that basically means 1,350 joules of energy is transferred or moves every second. Now what's the last bit? Per meter squared. Joules per second per meter squared. So what do you think that means? Well, it means for every meter squared, 1,350 joules of energy is transferred. So what we can say here is that if the sun is falling on it, 1,350 joules are falling on it every second for every meter squared. So now we want to find out what's the total amount of energy that it falls on it over a 6-hour period. If this is the size of the solar panel, we need to figure out, first of all, how many seconds the sun is falling on it for and how many meters squared there are. So the area of the panel is 4 by 4, which is 16 meters squared. So we have 16 meters squared. We have 6 hours of sunshine, so the total time in seconds would be 6 multiplied by 60 minutes in an hour, 60 seconds in a minute, which gives us 21,600 seconds. So now this amount of energy falls on it for this amount of seconds on this amount of meters squared. So it's going to be 1,350 per second, so multiplied by 21,600 per meter squared, so multiplied by 16. And you'll get an answer of 466.56 megajoules. So what I'm trying to get across to you there, and hopefully that made sense, is that units are really, really important. And if you understand what units mean and how units are written, you can solve questions without actually knowing too much about the content, with a little bit of logic as well. So what is the solar constant then? And if this didn't make sense now, once I tell you what the solar constant is, you can go back and watch the video again from the start. Basically, we have the sun here and we have the earth over here, and we get all our energy from the sun. Now, the amount of energy the sun gives us is fairly constant throughout the year. Now, what happens is the earth tilts towards the sun in summer, and then when it moves around the sun in the northern hemisphere, we're tilted away from the sun, so we get winter and summer. But on average, the amount of energy the sun gives us is fairly constant. The amount of energy it gives us is known as the solar constant. Solar because it comes from the sun, constant because it's fairly constant. And it's 1.37 kilowatts per meter squared. So what does that mean? It means 1.37 kilojoules of energy is falling on every meter squared of the earth every second. That's what that unit means. Now this does change. It changes depending on how much energy the sun is giving out, because it does actually change slightly depending on the activity in the sun itself, and also things like cloud cover, what's the cloud cover on Earth, and the Earth sometimes is closer to the sun and sometimes it's further away because it has an elliptical orbit. It's not a perfectly circular orbit. So this is just a rough approximation, but in questions they'll tell you what the solar constant is. Now what do you need to know? You need to know how to do examples like I just did up there, and you need to know this definition. The solar constant is the amount of solar energy striking 1 meter squared of the Earth's atmosphere every second. It's known as the solar constant or solar irradiance. One thing they don't have in that definition, which they should have, is it's at 90 degrees it's perpendicular to the Earth's atmospheric surface. So it's at 90 degrees to the Earth's atmospheric surface. So sorry, it doesn't take into account cloud cover and stuff, because it's how much energy is hitting the top of the atmosphere. And then cloud cover, etc., is going to affect the weather underneath. So is the sun's energy being blocked by clouds, or is it not? So that's the solar constant. Really, really small kind of section of the course, and if it comes up in a question, it'll come up either in question 5, just as a 7 marker, or as a small part of a question. So have a look at that example again if it didn't make sense the first time. The next thing I want to do is another really small bit of the course, and it's called U-values. And I hate when they put in these sections because they're kind of unrelated to everything else, and it's basically just a definition that you need to learn. So when houses are built, insulation is used to keep the houses warm. But what builders do, or engineers do, once the house is built, this is a wall, is they look at all the materials that has been put into the wall. So has aero board been used, or has a different type of insulation been used, is the cavity wall, etc. And what they do is they look at the materials that have been used, and they assign the house a U value. And what the U value basically does is it tells you how good an insulator that wall is. Is it good at keeping heat in, or is it bad at keeping heat in? Now, if the house has a high U value, it's a good conductor. And remember, a good conductor allows heat to travel through it easily, so therefore it's a bad insulator. So if you live in a house which has walls which have a high U value, you'd have to spend a fortune to heat it, because you'd be losing a lot of heat through the walls. If the house has a low U value, it's a good insulator. So that means as heat from the inside tries to move out, very little of it gets out. So in that house would be well insulated and would stay warmer for longer. So the definition of U value is, it's the amount of heat energy that can be transmitted across 1 meter squared of its surface every second, so long as there is a temperature difference of 1 Kelvin on each side of the material. It's measured in watts per meter squared per Kelvin. So let's say, and you don't need to even know this much detail, but let's say a house has a U value, or a wall has a U value of 2 watts per meter squared per Kelvin. What that means is, let's say that wall is exactly 1 meter squared. Every second, 2 watts of energy can move from the inside to the outside. 2 watts of energy, or 2 joules every second, for every 1 meter squared. Now this per Kelvin means for every Kelvin difference in temperature. So what I mean by that, and this is hard to get your head around, let's say the temperature here is 300 Kelvin and the temperature here is 299 Kelvin. There's a 1 Kelvin difference in temperature here. So that means every 1 meter squared will lose 2 watts of energy for every 1 Kelvin difference. So every second this wall would lose 2 watts of energy, or 2 joules of energy. If the temperature difference became 298, now the temperature difference has doubled, so it wouldn't just lose 2 joules of energy every second, it would lose 4 joules of energy every second. 4 joules every second, because now there's a temperature difference of 2. So it's 2 joules of energy every second for every 1 meter for every 1 Kelvin in the difference. So it's really tricky to get your head around that, but they tend not to ask questions about this. It tends to be the definition that you need to learn. And I'll give you some example questions today for you to practice.